US Physics Olympiad, year 2015, USAPHO, final exam. Problem B1. This problem is divided into two parts. It is possible to solve these two parts independently, but they are not equally weighted. Part A. An ideal rocket, when empty of fuel, has a mass mr and will carry a mass of fuel mf. The fuel burns and is ejected with an exhaust speed of Ve relative to the rocket. The fuel burns at a constant mass rate for a total time Tb. Ignore gravity. Assume the rocket is far from any other body. Question 1. Determine an equation for the acceleration of the rocket as a function of time t in terms of any or all of t, mf, mr, ve, tb, and any relevant fundamental constants. Question 2. Assuming that the rocket starts from rest, determine the final speed of the rocket in terms of any or all of mf, mr, ve, tb, and any relevant fundamental constants. Solution for question 1. Because momentum is constant, we can write that mv is a constant. So we can take first derivative from this expression, and we have this equation. But mass equal this expression, and dm over dt equal this expression. So now we can write what is the acceleration. So acceleration equal dv over dt, or this expression, which is answer for question 1. For question 2, we can rewrite this formula in form of this equation. Now we can take a full integral and find that speed v equal this expression when we use all fuel. That's the answer for question 2. Part B. The ship starts out in a circular orbit around the Sun, very near the Earth, and has a goal of moving to a circular orbit around the Sun that is very close to Mars. It will make this transfer in an elliptical orbit as shown in bold in the diagram below. This is accomplished with an initial velocity boost near the Earth, delta v1, and then a second velocity boost near Mars, delta v2. Assume that both of these boosts are from instantaneous impulses, and ignore mass changes in the rocket as well as gravitational attraction to Earth, to either Earth or Mars. Don't ignore the Sun. Assume that the Earth and Mars are both in circular orbits around the Sun of radii Re and Rm equal Re over alpha respectively. The orbital speeds are Ve and Vm respectively. First question. Derive an expression for the velocity boost delta v1 to change the orbit from circular to elliptical. Express your answer in terms of Ve and alpha. Second question. Derive an expression for the velocity boost delta v2 to change the orbit from elliptical to circular. Express your answer in terms of Ve and alpha. Third question. What is the angular separation between Earth and Mars as measured from the Sun at the time of launch, so that the rocket will start from Earth and arrive at Mars when it reaches the orbit of Mars. Express your answer in terms of alpha. Solution for question 1. First of all, we can find what is the speed around Sun. We use this formula for centripetal force, which is equal to force of gravity. From here we can find that speed equals square root from g mass of Sun over radius re, and for the same reason we have speed Mars is this one, or using coefficient alpha we can express it through speed Earth. These expressions we will use later. So this problem we can find directly using energy conservation and momentum conservation, but this is the long way. I can show you just formulas for that, but you could solve them yourself. I will show you a shortcut. First equation is angular momentum conservation. If speed v1, that's the speed of this rocket just in shortest position on a distance re, we multiply it by a radius of orbit of Earth, and that's equal to v2, which is speed in point of Mars orbit, and multiplied by distance from Mars to Sun. That's angular momentum conservation. And also we have energy conservation. For energy conservation we have this expression that full energy of a rocket, which is kinetic energy plus potential energy in closest point, equal to kinetic energy and potential energy in furthest point of this ellipsis. And if we have these two equations and we have two unknown velocities v1 and v2, we can find them through expression of square root from gm, and later use to find what is delta v1 and delta v2. But this is kind of a long story. I can show you a shortcut. If you remember third Kepler law, from this law we can conclude that period of rotation depends only from size of big axis of ellipsis. In our case that's re plus rm. But not only period depends from this size, also full energy depends only on this size, re plus rm. And this is the shortcut. So to find what is the full energy, we can use this expression. So if you can see, the total energy on the elliptical orbit equal to this expression. That is from one hand, and from other hand that's equal to kinetic energy in the closest point plus potential energy in the closest point. That will be this expression, and from this expression we can find immediately what is v1. So from this equation we can find that v1 equal this expression, or using v1 and alpha we can write delta v1 equal this expression, which is answer for question 1. For question 2 we have similar solution. Due to symmetry we can write that v2 equal this expression. We just exchange re and rm, and finally that's equal to this expression, and finally we will get for delta v2 we have this solution, which is answer for question 2. Solution for question 3. Here we can use a third Kepler law to solve this problem. From third Kepler law, we have time to travel for this rocket divided by period of Mars. That's equal this expression or this expression. For this time, Mars travel by angle 2 pi multiplied by this relation, which is this one, and the rocket travel for angle pi. It means that the total angle between Earth and Mars, as seen from Sun, in time of launch equal this expression, which is the answer for question 3.